Hello. So in this video we're going to look at an application of the sampling distribution for a proportion to a business application. So when a shipment of fragile computer components arrives at a distribution center for inspection, a random sample of 150 components is selected and examined for defects. The shipment will be rejected if more than 5% of the sample is defective. Well, suppose that 8% of the shipment is defective. What's the probability that the shipment will be accepted? That is, what's the risk of getting a sample that is under the cutoff proportion of the defective computer components in the shipment, and because of this, accepting a bad shipment? All right, so first, what's the trait? The trait is whether a computer component is defective or not. So there's your trait. And it's a yes-no trait. It either is defective or it is not. Now, the population is all the computer components, right? Fragile computer components. That's your population that you're testing. And then here, 150 is your sample size. It's how many are tested and seen, do they have the trait or not. Now, between the 5 and 8%, which do you think is P and which do you think is P hat? Go ahead and pause the video. All right, so here, if you see, it says no if more than 5% of the sample, so 5% is associated with the sample, 5% is P hat. Now we're saying that suppose that 8% of the understood entire shipment is defective. That's P, okay? Now, so let's take a look then at what they're asking. They're wondering if, although the truth about the entire population of computer components is 8% are defective, is it possible to get a sample where 5% or less are defective and you think that the shipment is good, so you buy it, and you really wouldn't have if you had known the truth? All right, so let's take a look at that problem. All right, so my info box, I have N is 150, P is 0.08, and P hat is 0.05. So let's go ahead and calculate the standard deviation of the samples, of the distribution for the samples. Okay, so that's going to be square root of P, and then either Q or 1 minus P. I always use 1 minus P. And so here we have 0.08, 1 minus 0.08 over 150. And I get 0.022, right? Now, so what that means, normally I tend to round. I'm going to go ahead and show both distributions where it's rounded and not so rounded. But normally what I do is I go ahead and draw the distribution of expected samples. Okay. The truth is 0.08. And normally I round to 0.02 just to make it a little easier on us. So I would have 10, 12, 14, 6, 4, and 2. But if I'm a little bit more accurate and actually go to use the 0.022, what you'd actually have is 0.08, 0.102, 0.124, 0.146, right? And here you'd have 0.058, 0.036, 0.014. So you can see what rounding does. The reason I round is I like to just get a general feel for what's going on, and then I use the more precise 0.022 in my z-score. But you're going to see why I wanted to go out a little bit more accurately in this. So now the idea is this. Is it possible to get a sample of 5%? Well, yes, it's in my distribution, right? So here's P hat. It's possible to get a sample where 5%, or what? Fewer, right? To accept the shipment, you'd have to have 5% or fewer that are defective, so you think there's not that many defective. So here you would shade to the left. And now what we really want to see is what's the probability of getting this sample? So you'd say, okay, how far is a sample of 5% from 8% standardized? And that is negative 1.3636 standard deviations from the mean. And now when I do normal CDF, I'm going to go from negative infinity to this value 0.05, but that's really going from negative 100 standard deviations to negative 1.3636 standard deviations, and I get 0.086, so let's say about 9%, all right? So what that means is there is a 9% chance of getting a sample where 5% or fewer, get this out of the way, computer components are defective. So in that case, 9% of the samples have fewer than 5% defective components in those samples. So you would think, oh, if you got one of these samples right here, you would accept the shipment, you would buy it. When in fact, the truth is 8%, and if you knew that, you wouldn't buy it at all. Okay, that's the idea. So there's a 9% risk associated with buying this shipment, right? So now I want to extend this problem a little and say, well, what would happen if we could do something to reduce our risk? What is the only thing we really have any control over? Well, is it the truth? Nope. Are we going to change our cutoff? No. The only thing we really can affect is the sample size. All right. So let's suppose that we double our sample size. Suppose we go to 300 instead of 150. Well, that's going to change our standard deviation, so let's go ahead and recalculate that. So now, the truth doesn't change, it's still 8%, but now I have a sample size of 300. And that's going to give me 0.016. Now, what's going to happen here, now I want to recalculate the z-score. And so I'm going to ask how far is a sample of 5% from 8%, but now standardized by the new standard deviation, and that's going to be 1.875 standard deviations from the mean. And again, we're going to recalculate the probability of getting that. And you're going to get 3%. So that's really quite amazing, because basically your risk went down from 9% to 3%. That's impressive, right? So if you can reduce your risk by 2/3, and all you have to do is double your sample size, that's really not that. That's a very good business decision, because really you're checking an incremental 150, right? An additional 150 computer parts. And how much might that cost? I don't know, maybe it'll take somebody an extra hour or two to check that. And how much do they make per hour? They probably make minimum wage to maybe $12 an hour. So to save that much money on an entire shipment, that's a very good business decision. Now let me just show you visually what happened. Well, here when we went out, here I'm using the more precise 0.022 and 0.016. And this distribution is more spread out because the standard deviation is larger. This distribution is a little tighter. And what I tried to do is go ahead and make this a little bit accurate. Now the truth is still the same. That's not going to change. So all your sample proportions are still going to pile up close to the truth. But notice here, like 0.058 is aligned so that it's a little less than 0.064, and here 0.048 is less than 0.058. So if you could put them both together on one number line, that's what I was trying to do. And essentially what you see is, to get the same sample on either distribution, it's a slightly different probability because of the area under the curve. Since this is much more spread out, this is the probability of getting that sample. Since this is tighter, there's a much smaller probability of getting that sample. And if I exaggerate that, it would be like the difference between something like this versus this, right? So your distribution is much tighter. So hopefully that clears up some idea of how you can apply this to business. Thanks for listening.